Again, welcome to Trillium Flow Technologies, Pump Bearings 101, selection guidance and unique solutions for overheating. Next slide, please. So we'll do the introduction. This is me, Simon Bradshaw. I'm not going to talk about myself. I'm going to talk about the important people here, Alessandro Nicchio and Francesca Rizzi, who are the Trillium experts who are going to present the technical details of this webinar. Alessandro is the after-sales engineering director at Trillium Pumps Italy. He has over 18 years of experience with Weir Gabinetta and latterly Trillium. He has education, mechanical engineering, and business administration degrees. And he was originally with R&D, but now focuses on aftermarket activities. Francesca Rizzi is a product manager at Trillium Pumps Italy. She holds a master's degree in mechanical engineering and has extensive experience in commercial operations, quality, and engineering. Next slide, please. So this is just a slide to kind of show you the breadth of what Trillium does. On the left-hand side, you can see all of the pump and valve brands that we offer. As I said, we design and manufacture many mission-critical pieces of equipment with pumps, both pumps and valves, and provide aftermarket parts and services to power generation, industrial, water and wastewater, oil and gas, and other aftermarket-oriented process industries. The pumps are in blue and the valves are in green. Just to kind of reel through some of the brands on the valve side, we have Atwood and Morrill, Autotorque, Batley, Blakeborough, controlled choke valves, Hopkinson, parallel slide, gate valves and glow valves, Saracen and Sabine safety valves, as well as Tricentric, triple offset, butterfly valves, and Redpoint. On the pump side, the brands that we're focusing on in this particular webinar are Gabinetta and Thermomechanica, but as you can see there, we also have Begerman, Flowway, Rotajet, Wemco, and WSP. On the right-hand side, that just shows the breadth of geographic coverage of Trillium. We have 21 facilities around the world, plus a global network of third-party sales and authorized service centers. That presence enables us to tailor our technical and commercial aspects of our products and services to suit your project needs. Next slide, please. This just talks about the heritage of Trillium Flow Technologies. Like a lot of companies in the space, we've been around under various names for a long time, 190 years or so. But as you'll see from this webinar, we're not standing still. We continue to add new products and services to make our customers' processes more efficient and productive. On this timeline, I'd just like to call out the Redpoint valves, which we added to the Trillium family in 2020. And in 2022, we were joined by Thermomechanica Pompe, enhancing our expertise in pumps for power, water, oil and gas, and servicing. Next slide, please. So here, this covers the pump portfolio in terms of what we offer. With the industries, if you want to go back, it jumped ahead, still back. Yeah, the industries are on the right-hand side. The pumps that we're primarily talking about today are in green, the between bearing pumps, but some of the aspects of the webinar are also applicable to overhung pumps. And with that, I'll kind of hand over to our subject matter experts to give you the technical details.
Okay, so let's start the webinar. Let's start our webinar presenting briefly the topic we will go through this session. We will first explain why bearing and lubrication are important for every pump user. Then we will talk about bearing and lubrication method selection. We will then present Trillium Flow technology solutions for specifically we will focus on between bearing pumps and including as well retrofit and upgrading option for existing equipment. Finally, after a short recap of all of what we will discuss in this webinar, we will have a question and answer session. So don't hesitate pulling through your question through the Zoom platform chat box. Now start to really start the webinar. So why bearings matter? Bearings and bearing housing are important to be discussed as they play a fundamental role in pump reliability and determining the operational cost, even though they are often neglected during technical discussion on pumps. Moreover, most of the pump parts are indeed inside the bearing housing assembly, and the design choices on bearing lubrication are key for trouble-free operation of the pump. So bearing primary function is in fact allowing shaft smooth rotation and with a minimum possible friction, maintaining the rotor aligned with the pump internals under all the effect of the load generated during the pumping action. As we can see from the picture in this slide, every pump rotor has to be supported in such a way that axial load, so the total forces acting in the direction of the shaft, and the radial load, so the forces in any radial direction, are transferred from the shaft itself to the structural part of the pump. The bearing housing assembly that comprises the housing itself, the bearing, of course, plus a number of other internal components, have the function of provide lubricant to the bearings, transmit the mechanical load received from the bearings to the pump casing and finally to ground with an adequate stiffness. And then they have the very important function of dissipate the heat coming from the bearing. And last but not least, prevent oil contamination. So ensure an environment where the oil and the bearing have the best possible condition. We can certainly define all this function as vital for the centrifugal pump. And of course, this is also can be supported by statistical data. In fact, as we can see from these two pie chart of this slide, the bearing and all bearing related issue are between the most critical components for pump reliability. Excluding more general categories and failures related to assembly, such as a mechanical seal, for example, bearings are the most frequent cause of failure for a single component and the most impacting voice of cost for pump repair for a single component. This is, of course, through the entire life of the pump. An issue in the bearing and the lubrication system is a severe threat to the pump reliability, as very often a damage in the bearings implies an immediate pump complete unavailability, or it quickly evolves into a severe issue. So given that bearing failures are critical for the uptime, it's worth investigating what causes a bearing to fail. And again, looking at the statistic on the bearing failure causes, we can see how lubricant condition, quantity, quality of lubricant fluids play a crucial role on bearing system life. It is important to note that while regular maintenance is for sure extremely important to ensure good oil quality, design choices in the bearing housing and the features that comes into the bearing housing are extremely important to avoid most of these common issues presented here, such as lubricant contamination, unsuitable lubrication, insufficient lubricant flow. In fact, top 4 causes can be addressed by specifically focusing the design of the bearing housing to these topics. And this is the reason why at Tritium Flow Technology we have decided to go through an extensive review and optimization of our bearing housing as a part of our continuous improvement processes that we have in place. So in order to better understand what are these crucial factors for bearing and lubrication design, we need to first define some key concepts and look at bearings in more details. So we can first classify bearings in the way they reduce friction, and therefore the method they are based on to accomplish the primary function, which is allowing shaft smooth rotation, as we have said. The first option is hydrodynamic bearings, presented in this slide, where the reduction of sliding friction is based on a film of lubricant that is created between the rotating shaft and the stationary part of the bearing itself. Hydrodynamic bearings can be arranged to withstand radial or axial load, but in both cases, it's the relative motion of the shaft respect to the pads combined to the peculiar shape converging geometry here that creates an oil wedge of and into this oil wedge a pressure distribution that actually counterbalance the loads acting on the rotor. Then we have the so-called anti-friction bearings, where the friction is reduced by interposing between a rotating inner ring and the outer ring revolving elements, such as ball or cylinder, just the one depicted here. So these bearings exploit the physical fact that rolling friction is noticeably lower than the sliding friction. Now, depending on the shape of the rolling element, these type of bearings can withstand only radial load, only axial load, or a combination of both. They are these type of bearing are the most widely used in machinery, and as they are very simple and cost effective in a wide range of speed and load carrying capabilities and combination. With both type of bearing, so whatever we are talking about, anti-friction bearing or hydrodynamic bearing, in any case, it is extremely important to have a proper lubrication. Let's first have a look to basic concept of lubrication, starting from a definition. So lubrication is the interposition of a fluid between two surfaces in contact or in relative motion. And depending on how low the relative speed, viscosity, quantity of lubrication combined in each application, we can have 4 different lubricant conditions in relation to the film thickness that is created. So at first, with high load, low viscosities, low relative speed, small quantity of lubricant, we have a very thin film that is not sufficient to separate the two bodies in contact. So the load is carried by the asperities of the surfaces. Basically, the film is definitely negligible. And in this condition, of course, we can expect very high coefficients of friction, as shown here on the vertical axis of the slide. And of course, as a consequent, immediate wear and damage of parts. Increasing the amount of lubricant, viscosity, and relative speed or with lower loads, then a lubricant film starts to separate the two bodies in relative motion. And now the loads are partially sustained by the oil film itself and partially still by the measured asperities of the surfaces. In this condition, with increasing film thickness, we have a deep reduction of the coefficients of friction that gets to a minimum as soon as we achieve the minimum separation of the two bodies. Further increasing the oil film thickness, so reducing the load, increasing speed and the lubricant quantities, we get thicker and thicker lubricant film. And we start seeing in this condition, of course, we don't have any contact between the two surfaces, so they are actually floating one over the other. So we have negligible wear, but we can see an increasing level of friction because as it's explained here, as the film thickness increases, we start see viscous forces into the lubricant film increasing and opposing to the relative motion, such as friction does. So that's the effect. And we have mechanical power, which is dissipated into heat into the oil film. In summary, the selection of lubrication method and the lubricant itself is aimed to achieve an operational point, which is, of course, the minimum of friction and the minimum of wear. So we want to operate basically in this area here. We are going now to see how we can best select the bearings, which type between the one available, and which lubrication methods are available for piping application. Over to you, Francesca.
Just before Francesca starts, just to remind all the participants, I see someone with their hand up. Please, if you have a question, put it in the Q&A box, which is at the lower end of the lower part of the Zoom chat window. Thanks. Sorry, Francesca. Carry on.
Simon, thank you, Alessandro. Recalling bearing and bearing-related issues chart, wrong bearing selection, unsuitable lubrication, and insufficient lubricant quantity account together for around 45%. For this reason, selecting proper bearings type and relevant lubrication method is crucial, considering the severity grade of bearing failure consequences we already mentioned. In addition, it is important highlighting how that for any rate with new operating condition or also product changes, a new bearing selection should be made. The bearing type and arrangement are selected in accordance with the more stringent criteria, for example, as expressed in API 610 Table 10, considering bearing speed limits as per bearing manufacturer declaration with also specific references to bearing type. Bearing life on the basis of bearing load amount and direction, pump bearing energy density related to pump rated power, and operating and ambient temperatures. Furthermore, considering any possible contamination from outside to the internal part of the housing and also application parameters, optional features are considered to best meet the specific requirements. On the next slide, we can see an example of a between bearing BB2 pump. Here the shaft is supported by 2 radial bearings and 1 axial thrust bearing. Bearings can be arranged in 3 different configurations, again on the basis of selection criteria: anti-friction rolling bearings, radial and thrust, hydrodynamic radial and rolling bearing thrust, or hydrodynamic both radial and thrust. With each type of bearing and as we have just seen how it reduces friction, different lubrication methods are applied. Grease or oil with anti-friction bearings, and self-lubrication or forced lubrication with hydrodynamic bearings. In general, anti-friction bearings are used with lower speed, load, and energy density. When mean bearing diameter per RPM is less than 500,000 and energy density is less than 5.4 million horsepower per RPM or 5 million expressed in kilowatt per RPM, typical for non-pipeline pumps from the API. When one of these conditions is not satisfied, hydrodynamic bearings are used in general with higher speed, load, and energy density. On the next slide, a brief overview of lubrication method. Starting with anti-friction, radial and thrust bearings are selected with speed and life within limits for rolling element. Then, considering the specific application, several lubrication can be applied. Grease used for low speed and power application and low temperatures, where high dissipation capabilities are not necessary, actually not very common within API. Lubricant higher viscosity assures greater adhesion. It allows easy maintenance. With the oil splash inside the bearing housing, there is always a bath, and rolling elements are directly in contact with the oil bath. On rotation, the oil is drawn up. Anti-friction bearings with oil splash are selected with low speed and power, since this method has low heat dissipation capabilities. It is important maintaining the correct level of lubricant. Too much oil will increase oil temperature, remembering viscous friction phenomena we mentioned before, and as a consequence, oil degradation and wear, while too low oil will cause dry running of the bearing. The next, the oil ring, there is a bath, and in addition, a metal ring is placed around the shaft. As the shaft rotates, the ring picks up some oil, spreading it onto the shaft and bearing housing internal surface, from where it flows sideways and lubricates the bearings. Heat dissipation capabilities are higher compared to the oil bath, so it is selected in case of higher speed and power. With the oil ring, the distribution inside the housing is critical, depending on the speed, the internal pathways, and on the level of lubricant itself. If too wide, the ring will be submerged and it wouldn't circulate the oil. If too low, the ring wouldn't pick up the oil. With the oil flinger, a disc is mounted directly on the pump shaft. It is designed to pick up the oil from the bath and to spread it into the bearing and into the housing. Flinger is an alternative to oil ring when specific requirements don't allow oil ring, or for example for offshore installation, but it works best at lower speed compared to the oil ring. With anti-friction bearings, using oil mist is an additional option. The oil mist is produced by atomization and transported to the bearing housing by compressed air. The system goes from a central reservoir to multiple points where mist is injected for also several machinery. In the pure oil mist, there isn't an oil bath, but the oil mist enters the bearing housing, lubricates the bearing, it runs away from the drain, returning to the lubrication console, where it is cooled and fed back to the system. It is not necessary any additional cooling system to the bearing housing that is pressurized, avoiding contamination from external environment, such as dust, dirt, particles, and so on. Pure gel mist is an option for oil ring and flinger lubrication. It is used to purge the housing that is under pressure and external particulate can't enter. In both cases, besides advantages such as less oil consumption in general and oil and housing cleanliness, main drawbacks are oil mist reservoir and generator costs and containment issues with sometimes possible environment pollution. For hydrodynamic bearings, they are used with higher speed, load, and power. We can see, here we can see an example of a hydrodynamic radial and rolling element truss assembly selected when radial bearing speed or life is outside the limits for rolling element, and the truss bearing speed and life are within limits and pump energy density is below the limit. With hydrodynamic bearings self-lubricated, the oil ring is added, enhancing oil circulating inside the bearing housing and allowing the oil film creation, supporting with journal bearings, the radial load and lubricating surfaces. Hydrodynamic bearings self-lubricated are best used for medium to low temperature services. On the next slide, we can see the last type of bearing lubrication. In the case of forced lubricated hydrodynamic bearings, lubricant oil is injected between bearing and the shaft surfaces, but by an external pumping unit. Forced lubricated hydrodynamic bearings support for this reason higher loads. Oil film always protects surfaces that are never in contact and there is no wear. The oil flows from the inlet into the bearing housing, oil supply in the picture, through the channel inside the bearing housing and to both the sleeve and the tilting pad truss bearing, and then it returns to the external unit. Here the oil is filtered, cooling is applied as necessary, and then it is again injected inside the bearing housing. Again, depending on the application, from hydrodynamic fixed profile up to tilting pad self-equalizing bearings can be selected to increase bearing performances. Forced lubricated hydrodynamic bearings, typically selected on multi-stage pumps with high loads and high speed and power involved, allow to have a reliable bearing assembly. On the other hand, must be taken into account additional complexity and cost for the external U-boil system and the tilting pad bearings themselves. After this brief overview, we highlight again that doesn't exist the beforehand perfect solution bearings and lubrication method, but proper selection, considering all involved parameters, is crucial for pump reliability to avoid the drastic effects of overheating, overloading, and dry running. Closing this section, here we have an example of Trillium Flow Technologies particular solution using hydrodynamic bearings product lubricated, specifically designed for power and water market through Thermomeccanica Pompe brand. Looking at the pictures, the product flows from the internal pump volute to both thrust and axle bearings, as highlighted with the blue arrows. The result is a fully self-contained pump casing with product lubricated bearings. The specific design is excellent with clean fluids. It avoids the cost and maintenance of bearing housings and requires only the mechanical seal and packing assembly. Main applications are water, water transportation, supply and distribution, seawater desalination, and booster services. Now let's go ahead to the heart of the webinar, presenting Trillium Flow Technologies' specific answer and exclusive solution to avoid, prevent, and when already occurred, to solve some of the main failure causes a pump owner faces: overheating, lubricant contamination, insufficient lubricant flow. Over to you, Alessandro.
Thank you, Francesca. So let's start recalling the statistic on major causes of bearing failure. The key concept is that 2 of the 3 top causes of bearing failure are strictly related to oil temperature. In fact, oil viscosity is the most important oil property to determine the capability of the lubricant fluid to create an effective film and reducing the wear of parts. And when the temperature increases, viscosity decreases, reducing in the end the chances to get a proper oil film thickness. So, and therefore having a tough contact between the parts in relative motion. Furthermore, the oil temperature is also a key aspect in determining oil life. The higher the temperature, the fastest oxidation reaction occur in the oil, decreasing the oil life, and therefore they increase actually the need of more frequent oil changes. Independent studies made by major oil producer state that just the 10 Celsius of oil temperature increase will halve the life of the oil. So given oil temperature is so critical, how can we manage it? There are several factors affecting the overall temperature into a bearing housing. Of course, we have to start analyzing the application and its constraints, such as speed, radial, and thrust load. All these input will determine a proper bearing type and size suitable for this application, as Francesca explained before. Once the selection of the bearing is done right, the design focus shifts to the housing itself, considering first of all its heat transfer capability. Because of course, the more the heat is transferred to atmosphere, the lower will be the temperature inside the housing. The way bearings are lubricated is also extremely important, as we have said. So proper circulation of the optimum amount of oil, so not too much, not too low level of oil, should be created within the housing, avoiding dry running as well as excessive stagnation of oil. Oil type and the oil volume shall also be designed and considered to ensure the right viscosity of the lubricant at the operating temperature. And of course, these choices have to be made in relation to the heat exchange capabilities of the housing itself. Once the core features of a bearing housing, that is namely the bearings and the bearing lubrication method, there are additional features to be considered. For example, when we are pumping hot fluid, additional cooling packages can be added to the housing to dissipate further heat coming from the pump casing or the shaft. And when it's the case, even the direct sunlight can increase the temperature. So sun shields should be considered whenever sun exposure can increase the metal temperature considerably. All these features and optimization are results of a continuous improvement program here at Trillium Flow Technologies, I was saying even at the beginning. So these processes we have in place based on robust processes, field testing, are continuously carry over to continuously improve the performances of our product under these aspects. So during one of these continuous improvement iteration, in addition to the classic finned housing we are used to see, we have developed a unique Italian patent pending design bearing housing aimed to boost the heat transfer and keep lower temperature of both oil and the bearing, exceeding API requirements for cooling. The innovative design we came out is very simple, robust, as well as effective. It consists in the use of aluminum heat sink connected to the housing, that increase the heat dissipation thanks to two main principles. The greater heat conductivity of aluminum compared to the carbon steel used for the bearing housing, and increase heat exchange surfaces as the heat sink are not subjected to the casting technological limitation in terms of thickness and length, and therefore these can be designed with the best, the highest heat transfer capabilities. The comparison, of course, this has been tested, and the comparison with the same bearing housing is presented here in this slide. So the new heat sink version, heat transfer capabilities, has been proven to be 15 to 20% better when compared to the classic casted finned version. The graph on the right side shows the reduction of bearing outer raceways of the bearings and the oil temperature as well in a real performance test run at different speed. So we can see that both bearing and oil temperature were 6 to 10 Celsius degrees lower for most common application pump that are running at 2-pole 50 and 60 Hertz. Again, we definitely need to stress the fact that though these may sound as a minor difference, it has in reality a big impact on oil quality. Oil life is expected to double every 10 Celsius temperature reduction. So in the worst case, we can state that thanks to this evolved design, the oil life can increase from 30% up to 100%. Furthermore, all these test data have been obtained in a relatively cold test condition as the heat and as the transfer capabilities increases with a difference of temperature with respect to ambient. So the spread between these two designs will increase when we will when handling hotter application. So the bearing and the bearing housing will stabilize at a higher temperature. In summary, the benefits of such lower temperature we can achieve with the new design is longer oil life. And again, remembering that major oil producer states that we can double the life of the oil if we reduce 10 Celsius the temperature of the oil itself. Longer bearing life as a result of the better lubricant film condition in between the rolling element and the races, or between the pads and the shaft. Less requirement of additional water cooling, both because of pump speed or because of pump and fluid temperature. So we can have the requirements for water cooling starts at a higher pump and fluid temperature. All these, of course, finally reflect into lower installation cost and, most important, lower operation cost. Longer mean time between failure and higher reliability of the pump. Now, this concept, the concept of the heat sink design, has been then developed into a complete line of bearing housing that is shown here. Example, comprising a mix of standard optional feature, so that each application and each requirement coming from different specific needs is foreseen and made easily available during the pump selection process. API 610 requirements, of course, have been considered, so we have a full compliance of API requirements, but we have also considered our ultra-centenary legacy brand experience coming both from Gabionete and Thermomeccanica brands. So we have blended all these together, creating this new line of bearing housing. And again, we have, of course, available housings for anti-friction bearing and hydrodynamic bearing. Now, regardless of the bearing type, all the housings are available with a 180 or 360 mounting interface to the pump. Of course, stiffness is an important parameter while discussing about the assembling interfaces. The stiffness of the housing itself has been studied through finite element analysis, considering the worst case between the two options, which is of course the 180 assembly mountings, satisfying the achieving enough stiffness for all the application. The criteria between to select between 180 mountings or 360 mountings should also consider other factor, most important of which is the type of API plan of the mechanical seal. So 180 mountings are best for process pump with multiple API seal plan that requires a lot of connection to the mechanical seal. So we need a lot of space to connect the pipe. This makes maintenance even much better and easier, while instead the 360 mountings are better for very high energy pumps or high speed application, typical, for example, of the multi-stage BB3, BB4, and BB5 type of pump. As Francesca has previously explained in the introduction, then the lubrication options are also very important. And again, we have foreseen several options, starting from the oil ring, which is the standard, as it has the best, let me say, capability of circulating oil in a wide range of speed. Then we have the Flinger with its pros and cons. Integral pure mist is of course available. And finally, there are options, of course, for the purge oil mist and high quality bearing isolator, because lubricant to avoid the lubricant contamination from the external atmosphere. So we can have a bearing isolator up to IP66 grade, so very effective in preventing water and particles enter the housing, and of course the purge system that pressurizing the housing avoids external ingress from the external environment. In very niche applications, such as pumping at very high temperatures, say in excess of 260 Celsius, there are additional features that can be added. So fans for the drive-in side, water cooling for the oil bath, toroidal roller bearings. These, instead of the standard ball bearing on the drive-in side, will allow shaft to freely expand under the thermal expansion because of the high temperature of the application. And last but not least, the inboard radial fan and relief on the assembly interface to reduce the heat flux from the hot casing, and allowing some higher forced air circulation in between the mounting flange and the casing. Again, of course, to limit temperature. It's important to mention then that for a good bearing housing, it's also features for and provision for monitoring what's going on into the bearing housing are extremely important. So let's see additional details on instrumentation with Francesca in the next slide.
Thank you, Alessandro. If bearing selection and bearing housing design are of basic and paramount importance, looking again at the bearing failure causes chart, we can see that there are additional significant failure reasons resulting in extremely serious consequences. In this sense, instrumentation equipment is crucial, allowing proper monitoring of the most significant variables related to insufficient lubricant quantity, contamination, overextended oil changes. In addition, proper monitoring is key, ensuring to carry out maintenance at the optimal time. Trillium flow technologies bearing housing are equipped with all necessary instruments, temperature sensor for both oil and bearings, vibration and positioning detectors, additional provisions for further instrumentation, including also oil quality measurement and any contamination detectors. Standardized across bearing type and bearing housings, Trillium Flow Technologies bearing housing instrumentation provision supports condition monitoring and allows predictive maintenance. On the next slide, we can see vibration monitoring that, for example, allows to detect failure such pump shaft misalignments or unbalanced impeller vanes that can have consequences from lack of efficiency to pump complete breakdown. For ball bearings are provided, they are provided with accelerometers, while sleeve ball and force sleeve assemblies, in addition, have the proximity probes. Here we have shown the recommended generic indication for proper monitoring instrument provision is then every time selected on the basis of the application. Besides vibration, it is crucial also temperature monitoring. Here we can see that for anti-friction bearings, temperature can be monitored by spring-loaded RTDs on outer races, hydrodynamic by spring-loaded RTDs or embedded sensors close to the white metal layer into bearing pad and bearing surface. Oil temperature is measured by RTD for ball and sleeve ball assemblies where an oil bath is present. Applying redundance logic, main temperature sensors can be doubled. Again, here we shown recommended generic indicators for proper temperature monitoring to be tuned for each specific application. Just to mention Cyclops 2 Trillium cloud-based solution with easy and secure access to data and relative analysis via app or browser. Cyclops 2 can be installed on Trillium pumps as well as on other OEM brands operating across several markets. It is flexible and modular. After the deep insight, understanding among Trillium flow technology solutions, in particular the bearing housing design and its huge benefits, in the next slides we will see two examples of Trillium flow technologies aftermarket upgrade options. Starting from Retrofit, that consists in general in modifying pump hydraulics, mechanics, materials, and monitoring equipment to solve an issue or to meet new operating conditions or to upgrade the pump. As Alessandro presented in the first slides, bearings and bearings-related issues are among the most frequent and serious failures for a pump, resulting in unplanned downtime, maintenance cost, reducing production, and so on. Bearing assembly retrofit is an opportunity to address issues root causes. Replacing old bearing housing with the evolved design, selecting the best option among several available, taking advantage from the improved cooling capabilities combined to the evolved standardized design. Applying a proactive approach, retrofit can be implemented during planned maintenance to replace existing obsolete bearing housing assemblies and upgrading them, increasing housing and so the whole pump reliability. On the next slide, but last but not least, we can see the second example that is related to overhang pumps. Trillium flow technologies overhang pumps are designed to allow rapid dismantling and reassembly. Through the back pull-out design, outdated bearing housing can be replaced with the upgraded ones, enhanced also monitoring provisions. Of course, the back pull-out design allows not only bearing housing replacement, but mechanical seal assembly and pump hydraulic parts can be easily removed and replaced with upgraded ones, for example, to renew them or to meet new operating conditions. On the next slide, on the chart, we can see that new back pull-out assembly is in accordance with the PI 610 last edition guideline for shaft stiffness for overhang pump types. Being the new back pull-out assembly parameters below the green line results in higher stiffness for the shaft assembly, ensuring lower vibration. In this sense, back pull-out is an easy solution to upgrade the whole pump, avoiding to completely disassembly, reducing pump downtime, and in general, increasing pump life and reliability. So, recalling you the chance to ask any question through the chat box, let's move towards the conclusion of the webinar. To recap, we started explaining how bearings and bearing-related issues are among the main causes for any centrifugal pump failures, seriously impacting on pump reliability. Then we focused on the contribution of the various reasons at the root of bearing and bearing-related issues, seeing the criteria to proper select bearings and lubrication suitable for application. And in the last two chapters, we showed Trivium Flow Technology solutions designed to avoid and solve the other major bearing failure causes, presenting the Italian patent pending bearing housing design. Trivium Flow Technology is a unique solution to solve real customer problems by lowering oil temperature and therefore increasing oil life, with consequent advantages: high-speed operation and hot services without water cooling, lower operating cost, and also lower initial installation cost, not using the water cooling line. Higher reliability, as on the wall lubrication conditions are improved. As a consequence, increased mean time between failure and easy maintenance, making actually possible to really increase the servicing life of the pump, reducing unplanned maintenance and increasing uptime. Now we are arrived at the end of the presentation, and today's webinar will be soon available on our YouTube channel, where you can find many additional topics. We have some of them on the slide. By thanking everyone for listening, we are going now to address your questions in the next remaining minutes. Please refer, in any case, to our contacts on the next slide for any following clarification you may have.
Thanks.
So over to you, Simon, for the questions.
Yes, thanks, Francesca and Alessandro, for a very detailed technical presentation. We have quite a few questions. I'm going to take the first one. Maybe Alessandro, if you can pull the deck back to where the instrumentation was, because the questioner is asking, what instrumentation do you recommend for the arrangement of hydrodynamic bearing, radial bearing, and rolling element thrust bearing? So basically sleeve ball. Maybe you could talk to that.
Okay, here basically we have put the general recommendation as standard, as minimum. Then as told, for every application, the best instrumentation are selected. We can have for sleeve accelerometers, 2 in general, and 2 or 3 for non-drive-in side and 2 on the drive-in side, with the addition of proximity probes. The same for the force sleeve bearing housing, where we have again the sleeve bearings with the additional proximity probes, also on the axial direction, and if necessary, also the key phasor.
And then for the temperature, I think that was a following slide, right?
Yes, also for the temperatures, we have the general recommended. For the ball, we have 1 RTD for DE and non-drive and side for the bearings, and the same also for the sleeve ball assembly and the forced sleeve assembly. We have RTD on both sides, with the possibility to have redundancy, to add more sensors. For ball and sleeve ball housing assemblies, where we have an oil bath, also several oil temperature detectors can be added as shown on the slide.
Okay. Thanks, Francesca. I think that covered the questioner's question pretty well. Next question. The questioner, I'm going to combine because the questioner's asked 2 questions which are related. The questioner is asking, what is your opinion on fitting axial displacement probes on a BB3 with anti-friction rolling bearings for axial load. And then the question is asked the same with regard to VS6 pumps. So do you want to take that one, Alessandro?
Yes, of course. If anti-friction rolling bearing for axial are used, then this means that there is definitely no movement no axial movement of the rotor. So installing a proximity probe is kind of a curious solution. So definitely, I would say it's not recommended. The proximity probes, as Francesca was saying, are used whenever you have the hydrodynamic bearings, and therefore you have a relative displacement and different oil field thickness. So that's why you are measuring. So where the rotor is basically floating, so that's why you're using proximity probe. With anti-friction bearings, if there is an axial movement, then it's probably too late. So we are not talking about monitoring. That probably just we are discussing about the failure of the bearing.
Yeah.
So the second part of the question was basically the same, but on a vertical pump. So the concept is the same. So depending, the driver is the type of the bearing. So if the vertical pump is equipped with an axial thrust, which is an hydrodynamic one, then you could have a proximity probe to see the steady state position of the shaft. So that's what is used for. So you want to ensure that the minimum oil thickness is created. But again, if instead the pump is it's a vertical one, but you have an anti-friction thrust bearing, again, definitely it's not needed having a proximity probe.
Yeah. All right. So we'll probably need we've got quite a few questions here. Let's see if we can kind of kick through them a little quicker. So the next question is, are the heatsink, talking about the aluminum heatsink, are they integral with the housing or are they fixed separately? I think that's a quick and easy one.
So being aluminium, so they are not integral with the housing. They are mechanically fixed to the housing. So that's it. Okay.
Next question. Is it recommended to have a key phaser on one end of the shaft or both ends?
Well, again, if you have two and they give two different signal, then this means that the shaft is basically two shafts. So definitely the answer is you need one, unless for very, very uncommon, I would say, application. I've never seen you want a redundancy over there. But in the end, you just need one in the entire train. So this means the pump and the driver, because they have to rotate at the same speed.
Yeah. Okay. Let's see, what else do we have here? There's one here. They're asking about the theoretical bearing life calculation based on HI standard or ISO standard. How does that compare to real life bearing performance? If it's okay, I'll answer this one quickly. Is that the studies by the STLE found that something like only around 10% of bearings reach their theoretical life. And there's a number of reasons for this, but the main ones are some of the ones that Alessandro and Francesca talked about in the webinar, which is the bearings are calculated with assuming certain parameters, particularly things like oil viscosity and lack of contamination. And obviously in the real world, that often is not the case. And then there's other factors like, incorrect assembly, poor maintenance, all of that other stuff. So it's not good, which is why we have this innovation that we're talking about today. Next question. Someone is asking about the self-lubricated bearings, product lubricated bearings rather. They're asking what material they're made of. Someone wants to take that.
So we can say we can say that in this application that are where the fluid is basically clean, so that's one of the circumstances where we have to use these, where we can use these product lubricated bearings. It really depends on the speed of the unit, but generally the reply I can give at the moment is that's non-metallic, so polymeric or advanced polymeric materials for the bearing, for the product lubricated bearings and sleeves.
Okay. Let's see how we're doing for time. Maybe we have had time for one or two more questions. Yeah. So there's a question here is asking what's the difference between hydrodynamic bearings and hydrostatic bearings? Are hydrostatic bearings used in pumps? That's an interesting one. I haven't seen that one before.
So I try to give a reply, and then Simon, we can see if we agree on these. So the definition is based on the principle you use to create the oil film. So hydrodynamic is based on viscosity, on the drag forces that create the rotation, and not by the imposing of an external pressure source. So even though the pressure is used to inject the oil in the bearings, at the end of the day, the pressure distribution in the oil film is not due by the oil injection pressure, but just from the kinematic conditions. So they are normally hydrodynamic bearing. That's why they call hydrodynamic bearing. Hydrostatic bearings, I have never seen one in pumps, say for the API market, but here we can have a bias. So Simon, what's your opinion on hydrostatic bearings? Maybe just on heavy rotors, when you have the startup condition, you could consider that hydrostatic operating conditions for a bearing. So lift off just for the main rotor before you start up rotation.
Yeah, I mean, I think you explained it better than I could. The only hydrostatic bearings are almost never used in pumps simply because our rotors for most pumps are not heavy enough. They are used on things like big water turbines, big horizontal turbines where the rotors are so heavy that if you try to start it up, the oil is all squeezed out and you would get metal to metal contact between the rotor and the bearings. So in that instance, they use an oil jacking system, a hydrostatic system, which pushes the rotor up by injecting oil under high pressure. That system is only for startup and shutdown and is used at no other time. Typically then it will transition over to hydrodynamic. So it's really rare, really rare. I've seen it maybe a handful of times. And I think that's about all we have time for, guys. So I'm gonna stop there. Thank you all for your participation. Thank you, Alessandro and Francesca, for such a detailed webinar. As Francesca said, it will be available on the Trillium Flow Technologies YouTube channel in a few days. Thank you, everyone.
Thank you.
Thank you.
Thank you.